Hey guys, we're going to do another example that we've seen in class a bunch of converting our atoms to ions. And I want to get a little bit more into detail of why certain things are the way they are. And we're going to talk about electron configuration and that charge and more of the meaning behind the charge when we're writing our symbol for our ions. The example we're using today is bismuth, and we're going to use that logical squirrel analogy to help us figure out what kind of ion bismuth is going to create. First off, let's look where bismuth is in our periodic table so we can determine where our logical squirrel is going to land in the road so they can figure out which option is best. Bismuth is in group 15, all right? So that means if you're in group 15, you have 5 valence electrons. Everybody wants 8, okay? So if we're going to scroll down here to our road, and our logical squirrel is going to go where all atoms go that have 5 valence electrons. All right, they're slightly on the right side of the road. 4 is right down the middle, as you can see between our center lines. And then we have our safe curbs, which are representing our stable ions with 8 valence electrons. And we have that on the far left and the far right. So our 2 options for this logical squirrel from our 5th position here is 1, 2, 3 to the right, or 1, 2, 3, 4, 5 to the left. What does it mean to go left and right? To go to the left means to lose. So this would mean that the logical squirrel loses 5 electrons. And to go to the right means to gain electrons. So we would be gaining 3 electrons if we chose to go this way. So our logical squirrel is going to always choose whichever requires the least amount of energy, all right? It takes less energy for us to walk 3 steps than it does for us to walk 5 steps. It's the same idea that our atoms use when they're making this decision. It's going to take less energy for an atom to gain 3 than it is to lose 5. So that's why our logical squirrel is going to choose to gain 3 electrons, all right? Bismuth, when we're writing our symbol for this ion that has just been formed, we always start with our element symbol, which is Bi, and then we're going to write our charge. So when we gain electrons, electrons are negatively charged particles. So we're always going to write the quantity, in this case is 3, writing it as a superscript. And then if we're gaining those electrons, we're going to actually have a negative charge. We're taking on more electrons, so we are going to have a more negatively charged ion, also known as an anion. To explain this a little bit better, I want to get into details of protons and electrons and the balance that we have. When we say a neutral atom, that's because we have 83 protons and 83 electrons. They're balanced out. If we were to take our protons minus our electrons, we would get 0. And that is our charge. And we all know that 0 charge is neutral, okay? Now, when we gain electrons, like we did up here, right? We're kind of making that unbalanced. So that's why we need to indicate that charge when we're writing the new ionic symbol, all right? So in this case, after we've gained 3 electrons, we have 86 electrons. So now we're going to be doing 83 protons minus our 86 electrons. Okay, after we've gained those 3, this is why we have this final charge. And as we know, 83 minus 86 gives us -3. All right, and that is where we get this indication from, okay? And the other reason, I just want to point this out because you can see our calculation here for math, is a negative number. The reason we put the 3 minus when we're writing our symbol for ions is because it's actually indicating 3 negatively charged electrons. All right, so it's not necessarily a -3 quantity. It's telling us 3 negative electrons more than our positive protons. All right. Last thing I wanted to point out was our electron configuration. I'm going to erase this. So electron configuration for ions is not quite the same as what we see when we're doing electron configurations for atoms. It's a little different because we are, again, changing the number of electrons. Electron configuration means exactly that. How are the electrons configured? If we were to do our electron configuration for bismuth, just as a neutral atom, we know it would look something like this. And I'll use the abbreviated so that I'm not spending a ton of time writing out the whole thing. We're going to see xenon 6s2. We're going to have to go through the F block. So that means we're going to do 4f14. And the D block is going to be 5d10. And then we find ourselves in the P block, back to 6p3. All right. So this is what the electron configuration would look like for bismuth. Neutral bismuth before we change the number of electrons. I want to use the same information that we got from our logical squirrel and pretty much just move it up to our periodic table here. All right, that logical squirrel moved over to the right 3 times, and that represents gaining 3 electrons. And that's exactly what's happening on this periodic table. Our electron configuration for bismuth is seen at the bottom of the screen right now. But when we gain those 3, we're like moving over 3. All right. This is why people talk about the noble gas configuration, because we are going to resemble a noble gas when we're writing this electron configuration. In this case, we're writing the electron configuration for radon. All right. So let's see what that looks like and how it differs. So bismuth ion will look like this. Again, we'll do the abbreviated version. 6s2, 4f14, 5d10. Looks the same thus far, right? But we're not ending up at the same spot. We're going to keep going 3 more spaces over till we get to radon, which means we're going to be 6p6. All right, so you can obviously see the difference between our 2 electron configurations. The first one is just for the neutral atom, and the second one is how it looks when we do it for the charged ion. All right, well, I hope this helped explain a few of the things that we're going over when we're talking about electrons and ions, and I will continue to go over this in class with you guys. Thanks.